Hello everyone, my name is Richelle Gunawan with my partner Chloe Evelley Thesman. We are from SMA Santa Laurencia School Alam Sutra, and we will be presenting about our project titled The Utilization of Waste Asian Green Mussel Shells per Navirides from Cilincing, North Jakarta, Indonesia as an alternative source for the production of bricks. To begin, there is a lot of shell waste being produced by the seafood industry, causing it to be disposed of incorrectly. The picture on the left shows the shells being disposed of incorrectly on the ground in Cilincing. There are many detrimental effects of the concrete industry on the world and the environment, such as carbon dioxide emissions and climate change. Because of this, we conducted an experiment by taking these shells to be utilized to create bricks, which could be used for a better processing facility.
The issues and problems we have chosen to analyze in this research are seashells have become one of the waste materials that are rapidly piling up, especially in coastal areas and countries where seafood consumption is very high. The disposal of said used seashells in landfills and or public waters causes many environmental problems. And not to mention, the concrete industry itself also has a variety of negative consequences on the environment. The purpose of our research is first to examine the materials within the Asian green mussel shells and determine whether it is a suitable substitute for the manufacturing of bricks, to investigate the difference in qualities of the two bricks, to examine the amount of shell waste that could be reduced in Cilincing, North Jakarta, Indonesia, and lastly, to find the production cost to make waste mussel shell bricks as compared to that of the concrete bricks.
For the research stages, first we collected the necessary materials needed, including the green mussel shells. Then we started to make both bricks and collected the data by comparing and testing the two bricks. We conducted 5 tests, which are the compressive strength, durability or impact, water absorption, hardness, and structure tests. After that, we analyzed the data and made a report on it. This is the data we collected after conducting the 5 tests. We calculated the mean plus minus the standard deviation or the range of the data for the impact, water absorption, and compressive strength test. For the hardness test, we checked if there were any visible imprints on the surface, and for the structure test, we checked if it was homogeneous, compact, and free from holes, lumps, or any kinds of defects. The results of the impact test shows that the waste mussel shell brick was able to withstand the impact from a higher point than the concrete brick, which is also proven in our t-test. This means that it can absorb energy better, making it tougher, stronger, and more ductile than the concrete brick. This may be due to the calcium carbonate having extremely strong electrostatic forces of attraction that exist in calcium carbonate molecules.
The results of the water absorption test shows that the waste mussel shell bricks has less of a weight increase than the concrete bricks, meaning that the waste mussel shell bricks absorbs less water, which is also seen through our t-test, thus proving it to be much more durable and stronger in weathering conditions. This is due to the calcium carbonate found in the waste mussel shells, being insoluble in water since it is hydrophobic, meaning it repels water.
The results of the compressive strength test shows that the waste mussel shell brick was able to withstand more compressive force applied on it as shown in our t-test. This means that the brick has a better capacity in load carrying compared to the concrete brick. This is due to calcium carbonate being used to build composites to make strong materials. This illustrates that calcium carbonate bricks can withstand more power in a compressive machine.
When doing the hardness test, there was a clear and visible imprint on the surface of the concrete brick, whereas on the waste mussel shell brick, there is only a slight visible imprint left, meaning that it is much harder. This is due to the brick containing calcium carbonate, which is relatively harder and stronger since its structure has stronger bonds compared to that of sand. In the structure test, we were able to observe that all 3 concrete bricks were homogeneous, compact, but there were lumps and holes found. Meanwhile, all 3 waste mussel shell bricks were homogeneous, compact, and also free from lumps, holes, or any other possible defects. As such, the waste mussel shell brick is a well-structured brick, while the concrete brick is not.
There are approximately 5 tons of shells laying on the grounds of Cilincing. Making 600 bricks daily with 1 kilogram of mussel shell waste reduces 0.02% of the waste per brick. 5,000 bricks can be made in approximately 10 days, potentially reducing all waste. Though it is uncertain as to how much waste could be reduced in a day and how long it would take to fully reduce the mussel shell waste as the number of waste product constantly increases.
Taking into consideration as to the lasting period of